Hello all, this is a review of the document called Free Body Diagrams, and it's meant to help you prepare to draw free body diagrams to analyze situations, to identify net forces or accelerations that are involved with the system. So this is a review of the steps that could be helpful. So you can pause and take notes if you need to, or review the document that you have. But essentially we're looking to find a dot to represent an object or the system, and then any individual forces that are added should be included here. Here are a bunch of different samples. The first one is a box of mass M rests on the counter. So this is called the functional diagram, where you just sketch out what's happening. You have a box just sitting on the table, and it's helpful if you can identify all of the things that the problem tells you explicitly. So if it tells you that it's at rest, it means that its velocity is 0. That's the thing you can note immediately. It doesn't tell you an actual number for the mass, but it does tell you that it has this mass. And we can assume that it's on Earth. Unless it says otherwise, we can assume that it's on Earth. And on Earth, the acceleration is equal to the acceleration of gravity. So though it's at rest, the net acceleration is 0, but you have gravity pulling down and the normal force pulling up. So the free body diagram that would match the situation has to be one where the sum of all of the forces has to be 0. And if it's resting and it's on Earth, gravity must be pulling down and something must be pushing up. If it's on a counter, that something can be the normal force. The next situation gives you a sample where a box is being pushed. So you have something giving it a push on a horizontal surface. And it is moving. So moves with a constant velocity. Means that its velocity is greater than 0, but its acceleration must be 0 because its velocity is constant. It also says that it has a friction surface, so you know that the friction is probably not, well, you know that it's not 0. It's got to be greater than 0, but the direction is probably backwards. This is an F. This is a force of friction pushing backwards, and this is the force of the push going forwards. So in this case, because it is something is causing it to be moved, something is pushing it in order for its motion to change, you have a push to the right. But because the acceleration is 0, you know that the friction to the left has to be equal to the push to the right. So in this case, because you know the acceleration is 0, that means the net force is 0. That means all of the forces have to add up to be 0. So in this case, you can see the push to the right has to equal the push to the left, and the force up from the normal has to equal the force down from gravity. The third situation gives you a box that just is pushed up against the wall. So here's the wall, this red line, and then you have a box, and then this individual is pushing it against the wall with a force. I shouldn't have used the letter P. I should use F sub P. And the box is not moving. That means that its acceleration is 0. If the acceleration is 0, then the net force has to be 0. So then all of the forces that are added together have to equal 0. And in this case, you have an up and a down and a left and a right. And the down is gravity. And because this is the surface, the normal force is actually to the left in this example. You have a net force to the left, because that is what is perpendicular to the surface. The push is to the right. And because the push is towards the wall will then push on the box perpendicular to its plane. So that's why it's called the normal force. And then that way, the reason it isn't falling down, even though gravity is pulling down, is because the upward force must be the friction that's coming from the rough vertical wall. So these would be the 4 forces present in a situation where a box is pressed up against a wall. This situation is sort of mind-numbingly, you have to think, what is really happening? So an elevator is moving, but if it is moving up at a constant speed, that means the acceleration is 0. If the acceleration is 0, that means the net force is 0, which means that the sum of the forces has to equal 0. Now, the elevator is the system that we're talking about, and the thing that is pulling it up is the cable or whatever, like rope or string pulls an elevator up. That's the force that's pulling up on something. And if the speed is constant, that means that the tension up is greater than the gravity down, is equal to, because the acceleration is 0. This up has to equal this down. So this is the free body diagram for an elevator traveling at a constant speed, regardless of whether it's going up or down. These two have to be equal if the speed is constant. The next situation is as the elevator is slowing. So in the case of an elevator moving up, the velocity goes from positive towards 0, which means the acceleration is negative. So you have an acceleration that is less than 0. The net force must then be downwards. So your gravity must be longer than tension, because the acceleration downward means you have a net force downward. So if this force of gravity, I'll just draw it over here. If the force of gravity were added to the force of tension, your resultant force, oh, that's the wrong way. So when these two forces are added together, you would end up with a force downward, a net force that is in the downward direction. So the way we add them is tip to tail. So the tip of this one to the tail of this one produces a vector this long and in this direction. So anyway, if you think about the forces that are being combined, if we're adding them together, the sum of the forces has to equal a force with a negative acceleration, which means the net force is down. And so gravity has to be longer than tension in this example. In this example, we're using the dot to represent the sign, which has a mass, and you have two cables. You have a cable up here and a cable over here. We're just imagining that it's held from like a building or something. The sign is not moving. If it's not moving, that means its acceleration is 0. That means the net force is 0. So if you were to add up all the forces together, they have to be 0. Now the only forces that are present on this, I think I labeled them over here as, this one is Ft1, so that's the force of tension. And this is Ft2. And then this one should be labeled as Fg. That's it. Those are the forces. The forces acting on that sign are Ft1 and Ft2 and Fg. Now, if it is not accelerating, all three of those need to be added together. So I had this like option to like copy and paste the force. So like if I cut this force out and put it over here, and I cut this force out and put it over here, and I cut this force out and I put it over here, you can see that this one plus this one equals this one. Like you ended in the same spot, not only in direction, but in magnitude. And this is just sketched freehand, but if you were super careful with a protractor and indicating all of the angles that needed to be represented, you could show, and it would end up in the same spot. So that all three forces added together would not produce a change. The sum of all of the forces would be 0. And in this way, you can show that the three forces acting on the sign are equal. They are equal. I'm not saying that each one is equal in magnitude, but when you consider the magnitude and the direction, all three of them produce a sum that is 0, exactly the same value of where you started from forces. The next question is about like an object that's on like a string that hangs. So a bob is a pendulum, so that if you pull it back and you let it swing, at this instant right here, what are the forces acting on it? And if you're going to drop something, it's going to accelerate. So its acceleration is not 0. It's not going to just stay at this position the whole time. Eventually it starts to move. So you should show a net force diagram that ultimately is not balanced. All three forces, whatever force is acting on this bob, are not in equilibrium. So if you're analyzing the situation right here, I put a little like coordinate plane where y is directly up on the string and x is horizontal. So in that case, your force that's pulling up is directly up, and then the force that's pulling down, so this is gravity, would pull this way. So if you rotate this little system so that the upward force is parallel to the string, because that's the force that's pulling up, it's called tension, and the direction of motion is in line with one of the axes. So this is what it would look like if you just drew it on top of this functional diagram. And that would be okay. You could draw a force diagram that looks like this. But if you rotate it like this is one of the suggestions in the little front page. If you rotate it like this, it shows you that the motion is going to be in this direction. So the unbalanced portion of this, I'll take these and draw them over here again. You should not draw components on free body diagrams. Tension up, gravity over, that means that this would be the resultant force. So the net force is the sum of those two, and it should show that it's going to have it's going to be oriented in this direction, and it's going to be this magnitude. We can figure that magnitude out by looking at the angle. Since we know the force of gravity, and we know this angle, we would be able to determine the force of gravity in the x direction. You would use trigonometry. You can see this would be the sine of this angle is equal to the x component. You would have to go over here. So this angle right here is equal to this angle right here. So the sine of this angle would be equal to the FGX over FG. So this would be the way you would solve for the magnitude of the net force, but we're not to do those kinds of questions yet. The most important thing that you understand is this force is going to accelerate. This net force causes an acceleration. The net forces cannot be balanced. The last question is a really challenging one because you have to consider how you are asking the question. If you are identifying the system as just one of the objects, you can probably get a little bit of a hint as to how the entire system would accelerate as a whole. So when you have these two separate masses on a pulley, this one, it says, is larger than this one. And so you're going to accelerate down. So this block is going to move down, and this block is going to move up. So if you were to consider each system independently, your object 1 has to have a longer gravity force than the tension force. And object 2 has to have a longer tension force than the gravity force. Now I drew this gravity up because on my system, if you define y as up and x is to the right, as this one moves down, it's negative. But as this one moves up, we're going to flip I flipped the coordinate system for the M2 to show that when these tensions are facing each other, they're going to be equal. This is a Newton's third law pair, so that if box 1 pulls on box 2 pulls on box 1. They're connected by a string. That tension has to be equal. And if we decide that down is negative, this pulley just changes the direction of the force. It doesn't change the magnitude of the force. So I could take this object and have them face each other. In free body diagrams, you don't need to draw internal forces. And so if the entire object is your system, if both objects are your system, really what you could draw is that the force would just continue in this straight line. So this string can be imagined as being a straight line without a pulley. And for the entire system, the net force is the sum of the force of gravity on object 2 and the force of gravity on object 1. you'll see that the force of gravity on object 1 is larger. So the entire system, both m1 plus m2, will have an acceleration equal to the difference between these two forces. So that's it for the sample free body diagrams. This page is a super helpful breakdown of how College Board could ask questions about a free body diagram. So in this example, this individual, his name is Carlos. He pushes a block across a rough surface with an F with a force. They don't say FP, but you can label it as F of the push. So if it's traveling at a constant speed, then you know that the net force is 0 because F net equals mass times acceleration, which means that the sum of all of the forces has to equal 0. So if the push has to be canceled out by friction, those two should be equal. And you can see that this diagram has little like lines, it's like a grid, to make it easy for you to show like this one is 3 blocks to the right, this one should be 3 blocks to the left. Gravity is 4 blocks down, so the normal force should be 4 blocks up. They don't ask you to give it an actual number. You can put whatever number you want, but the key is that the upward and downward forces have to be equal, and the leftward and rightward forces have to be equal. The next set of questions is a sample of how they would ask a free response question. So if it says, we'll look at the question here. He is asked to derive an equation that relates the force of gravity and the normal force from the surface exerted on the block. So you're trying to derive an equation between these two things. This is the goal. Try to get these two as the things left over in the equation. And so they show you the steps necessary, but then they ask you to explain what's done. So almost for every single time you're supposed to analyze forces, you should consider what is the situation for Newton's second law. Is there an acceleration? And if yes, then the sum of the forces must not equal 0. If there is no acceleration, the sum of the forces do equal 0. So we're going to start this idea with Newton's second law, which says the sum of the forces exerted on an object is equal to the object's mass times the acceleration. So you're just using words to describe this math. The next step in the derivation that's provided says that the sum of the forces, and Fn is the normal force upward, and Fg is the gravitational force downward. So these are the forces acting in the y direction. And so the sum of the forces is going to equal the object's mass times its acceleration in the y direction. So my explanation says that there are 2 forces in the y dimension, normal force and gravity. In the y dimension, up is positive and down is negative. That's why this is a negative sign. We're adding the forces together. It's literally the sum of the forces. It's just that normal force is a positive force and gravity is a negative force. That sign clarifies the direction. Now the box is not accelerating in the y dimension, so the sum of normal and gravity must be 0. The next step says that it substitutes 0 for the whole product of mass times acceleration. So therefore, normal force plus gravity must equal 0. If the sum of Fn and Fg is 0, then the magnitudes of the 2 forces are equal. So that's a sample of a derivation that they would ask. This follow-up question gives a different scenario, and it is tricky unless you actually spend the time to use a free body diagram to think about it. So the next kid claims that if Carlos pulls with a string at an angle, he says that the velocity of the block is constant, so that the net force exerted on the block must be 0. Therefore, normal force equals gravity, and the force of friction equals the applied force. While that was true for the situation below, it's true that the net force is 0 because the block is not accelerating. However, in this situation, it is not true that the normal force equals gravity or the push equals the friction, because each dimension now has this pull is at an angle, which means that it has components. So you have to analyze the components to verify what the friction or normal forces are equal to. Your weight cannot change. The force of the pull will be given or can be determined. But normal and friction are called passive forces. They exert their force in response to a push or a pull or a force acting on it like gravity. So when the pull is directed up at an angle, the components must be analyzed. If the block's on Earth, its weight doesn't change. And we do know it's traveling at a constant speed, so you have to add all these forces together to get to zero. But in this case, because the y dimension has now three forces, you have gravity down, and then you have two separate ones that are up. You have the normal force up, and because this pull was at an angle, you have a little bit of a pull in the y direction. So this pull is really the FP in the x direction plus the FP in the y direction. So now you can see that Fn and Fpy are the positive versions of the forces in the y direction, and Fg is the negative version in the force in the y direction. So Fn is actually smaller than Fg in this case because the sum of all the vertical components must be zero. So if you were to add Fn and Fpy together, that would equal Fg by itself. Similarly, Ff has to be smaller than Fp because if you look, this is the hypotenuse of this little triangle. The rightward force of Fpx equals Ff because the net force is zero. But you can see, just by looking at the triangle, this line is longer than this one would be because this is a right triangle, and that's the hypotenuse. So in this case, friction is smaller than the pull because friction is to the left and pull is to the right. The push is to the right. In this case, the x component of the push has to equal the force of friction, not the push overall. So it is true that the net force is zero because the velocity does not change. However, because this force is now at an angle, you have components that need to be added together to cancel out. So that's a review of this document regarding free body diagrams. This little checklist right here is super helpful if you can think of these are the things that you're supposed to do. So in this case, we answered the question directly by saying what was wrong with the statement, and we identified how to correct it. The law that is always true is Newton's second law. The sum of the forces is equal to the mass times the acceleration. This specific situation shows that the pull is up at an angle, and so you need to use components. And the vocabulary that is important for this one would be things like the normal force, or the x component of the push, or the y component of the, or pull, I should say. The y component of the pull, force of gravity, the normal force, force of friction. Those are all reasonable vocabulary terms to use to answer this question. So this would be a 5. I'm sure of it. If you were to answer this, this would get full credit for a problem like this on an FRQ. Okay, good luck. Let me know if you have questions.